Have you ever stopped to think about why an explosion happens in a fraction of a second, but a piece of iron takes, years to rust? It's not just about if a reaction can happen, but it's all about how fast. And today, we are diving deep into the science of chemical speed, kinetics.
So let's start with the classic puzzle. We've all heard the phrase, a diamond is forever. But is it really? Chemically speaking, the answer is, well, it's a surprising no. And this sets up a fantastic mystery that only the science of speed can really solve.
So here's the twist. There's a whole field of chemistry called thermodynamics, and it basically predicts that diamonds, which are really just carbon atoms arranged in a special way, should eventually spontaneously turn into graphite. Yeah, the same stuff that's in your pencil. Why? Well, because graphite is just a much more stable, kind of happier, lower energy form of carbon. So what gives? We've got a major paradox on our hands. One part of chemistry says diamonds should change into graphite, but our own eyes, and hey, the entire jewelry industry, tell us that they just don't. The key to solving this whole thing is understanding the difference between possible and fast. Here's how you break it down. Thermodynamics, on one hand, just asks, can this happen? It's a simple yes or no. Is it feasible? But chemical kinetics, our hero today, asks the really important follow-up question. Okay, if it can happen, how fast? And that focus on speed, that's the key that unlocks our diamond mystery.
So our main tool for this investigation is chemical kinetics. The name itself comes from the Greek word for movement, which is perfect because it's all about studying how fast reactions go and the step-by-step paths they take to get from A to B.
So how do we actually clock a reaction's speed? In kinetics, we talk about the rate of reaction. But what does that really mean in plain English?
Okay, think of it just like the speed of your car. Instead of measuring how your distance changes over time, like in miles per hour, we're measuring how the amount of a chemical, its concentration, changes over time. So we can watch how fast our starting ingredients are disappearing, or how fast our final stuff, the products, are showing up. Same idea.
Let's make this super simple. Imagine a basic reaction where our reactants, we'll just call them R, are turning into our products, P.
Take a look at how this plays out. Right at the start, time zero, you've got 100% reactants, nothing else. But as the clock ticks, those reactants get used up and products start to appear. The reaction rate? It's literally just a measurement of how quickly these percentages are changing. That's it.
Okay, so if reactions have different speeds, what's controlling the gas pedal? What are the knobs we can turn to make a reaction go faster or slam on the brakes? Well, it usually comes down to three main culprits.
And here they are, the big three: concentration, temperature, and catalysts. You can think of these as the main control dials for pretty much any chemical reaction out there. Let's take a quick look at each one.
First up, concentration. This one is pretty intuitive, right? If you pack more molecules into the same space, they're just going to bump into each other way more often. It's like a crowded room versus an empty one. More collisions mean more chances to react, which means a faster reaction. Simple as that. Next up is temperature. And this is wild. Here's a great rule of thumb to remember. For a whole bunch of reactions, the rate just about doubles for every 10 degrees Celsius jump in temperature. Why? Well, when you heat things up, molecules move faster. They don't just collide more often, they collide with a lot more force.
A concentration and temperature, they aren't the whole story. The biggest factor, the real boss here, is this invisible barrier called activation energy. Okay, imagine you have to push a huge boulder over a hill to get it to roll down the other side. The energy it takes you just to get that boulder to the very top of the hill, that is the activation energy. This chart shows that energy hill perfectly. See the reactants on the left? To become products on the right, they have to get enough energy to make it all the way to that peak in the middle. That peak is a super unstable temporary state, and the amount of energy needed to get there, the height of that hill, is the activation energy.
So how can we make that climb easier? That's where catalysts come in. A catalyst is like a chemical matchmaker. It doesn't push the boulder any harder. No, instead, it finds a shortcut. It's like it digs a tunnel through the hill. Your body is full of them, by the way. They're called enzymes, and they speed up reactions that would otherwise take forever.
Now look at what that catalyst does to the energy hill. The peak is just lower. It's a much easier climb. And because this new pathway takes way less energy, a ton more molecules can make it over at any given time, and the reaction just takes off, going way, way faster. Okay, so we've seen the big picture. Now let's zoom way in, all the way down to the molecular level. We've been talking about collisions, but what actually makes one of these collisions work? The answer is in something called collision theory.
The basic idea is simple enough. For molecules to react, they have to physically smash into each other. But, and this is the whole key right here, most of the time they just bounce off each other with no reaction at all. So what makes a collision effective?
For a collision to actually work and create something new, two things have to be perfect. First, the molecules have to hit each other with enough energy. That's our activation energy hill we just talked about. And second, they have to hit each other in exactly the right orientation, like two puzzle pieces clicking together. If you're missing either one of those, it's a dud. They just bounce apart, no change.
All right, let's bring it all back home. How does this science of speed actually apply to the world around us? You know, from that diamond mystery all the way to the food on our dinner table? And here it is, the solution to our paradox. Turning a diamond into graphite? Totally possible, thermodynamically. But it has a ridiculously, enormously high activation energy hill. The energy you'd need to start breaking those super strong carbon bonds is just immense. So the reaction rate is so unbelievably slow, we're talking billions of years, that for us, it's basically zero. A diamond is forever because its decay is kinetically forbidden.
And this stuff isn't just about diamonds. We use kinetics every single day. We're manipulating reaction rates to control how fuel burns in an engine, to make dental fillings that set in minutes, to slow down the reactions that make food go bad when we put it in the fridge. Mastering chemical speed is absolutely essential to modern life.
And that pretty much wraps it up. We've seen that how fast something happens is every bit as important as if it can happen. From the sparkle of a diamond to a flash in a test tube, it is all governed by the rules of kinetics. So I'll leave you with this thought. Now that you know the rules, what process out there would you want to speed up or maybe slow right down to change your world? Thanks for joining me.